Okay, so we want to talk about the laryngeal source. What is the laryngeal source, and how can we actually figure out what it is and what it sounds like? So, to understand this, we need to go back to the source filter model. If you've had other classes with me, we've talked about the source filter model quite a bit in 205, also in 310, and we've mentioned it a little bit in this class as well. So, we've got our power source, which is behind my head. That's not great. Okay, so we've got our power source, which is the lungs, right here. So that's the power source. You're taking in air and you're forcing that through the vocal folds to create a sound. So that's the power source. The vocal folds themselves are the sound source. They're producing a buzz. And then that, let me get rid of my head again, because it's in the way again. There we go. So then that leads us to the actual production of sound. So we have this glottal airflow, right? So this is the vocal folds are opening. They begin to open here, so air comes out, and then they begin to close. So then we have a reduction of the pressure or the airflow that we're seeing here. And this is happening right here at the larynx. What happens after that glottal source, it goes up through this apparatus here, and it comes out as a speech signal. So there's a lot of steps from here to here, and we want to recover what's going on here. We want to figure out what's going on at the glottal airflow portion. We want to see what's happening at the larynx. And so we know, in theory, we know that it's producing a buzz, and it's got harmonics that gradually roll off. They decay as they go on. We've got a fundamental frequency here. We've got multiple harmonics that get lower in power as they move up the harmonic series. That's multiplied by a filter. The filter is given to us by all of our, I was going to say vocal apparatus. That's not exactly true. Our effectors, our speech effectors, the vocal tract, all of these things from the larynx out. So we've got this filtering system here. And what we get is the speech output like this. So we've got formants right here and here and here. So we still have a fundamental frequency, but now we also have formants that correspond to the filter, just like we talked about last week, and just like you guys made in the assignment at the end of last week's content. So, all right, let's move on. Okay, so, what is the laryngeal source? This is what we want to know. We know that it is exactly the beginning of speech. We have the power source, which is breathing, but the power source has to go through the actual sound source. So this is like the model on which all of our speech is actually built. So you've had 310, and you should be familiar with these different structures. So here's the larynx, where our sound is produced, comes up through the pharynx into the mouth. For some vowels and consonants, we use the nasal cavity as well, and then it comes out here, and we have a speech signal. So this is kind of what we just talked about. So there's a few different ways that we can actually measure what's going on at the larynx. So one of these ways is with direct measurement. We can use what's called nasoendoscopy or FEES. We talk about it in 310 as FEES, which is the flexible endoscopic examination of swallowing when we're talking about swallowing. But essentially, you just use a nasoendoscope, goes up the nose and looks down at the larynx. So you can use it to visualize swallowing. You can use it to visualize phonation, any of these things. You're still looking at the vocal folds in both cases. So that is one of the ways. And what we want to do is measure the opening. You can see this is like snapshots of speech actually happening. So here's the closed phase of the larynx, the vocal folds, and then here is where it begins to open. notice if you remember from 310, we talk about how it doesn't open, exactly totally symmetrically. It starts more down here and then moves further up. So you can see that it starts down here, and then the opening begins to move until the entire vocal folds are separated, approximately symmetrically, and then it begins to close. But you can also see that it doesn't close quite symmetrically. The bottom is coming together more quickly than the top, and then it's in its closed phase again. So this is direct measurement, right? We can actually watch what's going on when someone is speaking. That's direct measurement. And here we're, again, measuring the actual opening. So we can measure the open time, the time that this is open, the time that it's closed, and the degree to which it's open. We can also do indirect measurement. One of the ways that we do this is called electroglottography, or EGG, not to be confused with EEG. And what we're doing here is we're actually just measuring the electrical signals, actually the impedance at the throat. So when the vocal folds are together, the current, there's less impedance. So if you think about touching a wire together, right? So the current will flow, there's no impedance. So then we can assume that the vocal folds are touching. When they're apart, there's more impedance, and so then we can assume that they're not touching. And so that's how we use EGG. That's indirect measurement. So let's go back. For this one, you have to have an endoscope up the nose, looking down. With this one, you got to be strapped up with this EGG equipment. This person is not only strapped in with EGG. They've also got a microphone and this pneumotachometer here, which we'll talk about in a second. So they're kind of like looking at everything for this person. But really what I want to focus on here is the EGG for this indirect measurement. Now this is all measuring the actual displacement of the vocal folds, right? That's what we're looking at in both cases. Here we're actually watching it, and here we're measuring an indirect measurement of the displacement. But we don't have to just do that. We can measure the actual output. We can measure the pressure and airflow of the output. So we can use a pneumotachograph like you sort of saw in that previous picture. This is what it looks like if you were a cartoon. But we can actually measure the different pressures and airflow coming out of a person. But we can also just use a microphone and actually look at the speech output. This is a really easy way to do it in a clinical setting. I mean, in a laboratory, we can use all of these different ways. Sometimes in a laboratory, we might use all of these different ways simultaneously, just to get a really good idea of what's going on. So we might have a look at the vocal folds intermittently, just take a brief snapshot. Then we might also have an EGG strapped to the throat. We might have a pneumotachograph equipment on the person's mouth and a microphone there to measure it as well. But of course, this makes the environment really not super natural, right? So if we want to actually look at natural speech, a microphone is probably the best way to go. It's not invasive. They're everywhere. So you can do really good experiments and not have people fall prey to that experiment effect, acting funny because there's an experiment going on. The other thing is in a clinical setting, like we were talking about, you can just pull your phone out and record a speech sample. Or if you have, access to a really good microphone, you can bring that along with you. It's not hard for me to bring this guy to my office or any other location. So if you know that you're going to collect speech samples, you can bring your microphone that day. Now there are some interesting things that we have to do once we have the recorded speech output, though. And oh yeah, microphone, which I had a plan. It didn't work out. It's what? Forgot my own joke. Whatever. So when we have a recorded speech signal, we don't know everything on this diagram, right? We don't know the glottal airflow. All we have is the microphone, the speech signal at the microphone. So we don't know the glottal airflow. We don't know what the source actually looks like. We don't know what the filter looks like exactly. We have to interpret it all from the speech signal. And how do we do that? Well, we can use something called an inverse filter. So let's back up a sec. This is what the filter might look like. As we talked about last week, our output here goes through the filter. We multiply the, sorry, not the output. We multiply our sound source by the filter, and that produces our speech output, right? So we know that this times this equals this. And this is what we end up with when we're recording. And we can impute what the filter might look like in this case. We could kind of draw an envelope on top of this, like that, and get an idea of what the filter is. Now, of course, it might not be exactly centered. The peak of that filter might be between these two lines instead of on top of this line. It just could be. We don't exactly know what the filter exactly looks like because the filter can only accentuate or dampen frequencies that are present. So if we're not giving it the exact resonant frequency, we don't know exactly where the peak is. So if our fundamental frequency isn't in harmonic alignment with the resonant frequency, we're not going to see the exact perfect resonant frequency. But we can get a good idea of where it is. So let's get rid of those. We're back to knowing nothing, except we can have an idea of what the filter might look like. So then what we can do is we can take the inverse of the filter. We turn it upside down. And so then instead of multiplying this presumed signal by the filter, what we actually want to do is basically take this and divide it by the filter, or multiply this by the inverse filter, right? So if we take our speech output, what we're actually measuring, multiply it by the inverse filter, then we should end up with something approximating the source. And in fact, that's what I have here for you to listen to. So over here, oh, you know, I think I might have put those in backwards. Oh, no, I didn't. It corresponds. Okay, so here's my actual speech output.
E-oo.
E-oo, right? That's just me saying E-oo. It's really obvious that it's an E and an oo. But here, I used prot to recover the source. And this is what the source sounds like. So that's the source. It's not perfect, right? Because we have to kind of impute where the actual filter might be. It's not perfect. You can almost, because you know that it's an E and an oo, you can kind of still hear E and oo in there. But if you didn't know that it was an E and oo, if you didn't have that top-down information, call back to 367 if you've had it, right? Top-down information. If you didn't have that top-down information, you might not know that it was an E and an oo. You might think that it was just two of the exact same tone. So what we've got here is just the buzz. We've recovered the source. So what I've got written here is basically what we just talked about. So we know we can estimate the filter from this based on what we know about the equations of tubes and perturbation theory, what we know about filters and how they work. We can guess at what the filter looks like. Then we can flip the filter, multiply the speech output by the filter, and then we get the source. Okay. Oh,
Ooh.
we'll listen to it again. Those sound so similar to me, so much less different than the E and the OO. Now, these aren't two different samples. What I did was I took the E and the OO and I ran it through Prot, which does exactly this procedure of multiplying by the inverse filter, and we've got the sound source. So the inverse filter, what about it? What does it do? So where the actual filter amplifies something, the inverse filter attenuates it. And likewise, where the filter attenuates something, the inverse filter amplifies it. So if we take a look at this, we see that this peak right here, which if you look at the source over here, it's no peak. It's been accentuated by the filter. What we want to do is multiply this one by where this filter is. So we want to cut this back down to size, right? And here, where we've got this dampening of a frequency, we've got a bump in the filter right here. So it's going to push these back up. It's going to cut these formats back down to size. And that's how you end up with this, the source signal. Okay, this is basically just kind of showing you again how it works. But here we've got all of our different tubes. This is the tube model of the vocal tract, right? So this is it saying ooh. If you look at, here's the actual speech apparatus. This is that kind of placed on there. This portion here, which comes out the back of the mouth, should actually be going downwards, but it's fine. It doesn't have to go downwards. The change of direction doesn't really change the function of the sound. So imagine that it was moving down. It'd be a perfect analog for the human, right? But kind of goes out the back. It's just a system of tubes, so it doesn't have to look right to be an accurate model. So we assume that a glottal frequency comes through here, so just a buzz going through here. It's being filtered by all of these, different slight differences in tube size, just like we have here. The musculature of our pharynx is tightening or relaxing in different ways. The velum is open or closed for different sounds. For the ooh, it's closed. And here we've got a rounding of the lips, tightening and rounding, ooh. So we've got ooh, and that comes out as a speech signal. Here comes up. Here we've got our output filter, the inverse filter, and now we've got our speech signal again. Okay, so is it always perfect? Of course it's not. You heard that the E and the OO with the little top-down information, you could still kind of tell that it was an E and an OO, so it's not perfect. In fact, the quality of what we're doing depends on how good the laryngeal source recovery is, depends on the quality of our filter estimation. So if you're not very good at estimating the filter, then you're going to have crappy output when you multiply by the inverse filter, right? Similarly, if you have a bad inverse filter, then you're not going to have a good time. These, to me, go, directly together. And then, of course, the output signal, the quality that you're measuring that is going to have a huge effect on how you're able to recover the laryngeal source also. So if you are recording at a low bit rate or you have a bad microphone or there's a lot of noise in the room, that's definitely going to impact what you can actually pull out. If the signal's degraded, you can't really figure out what the filter looks like to make an inverse filter to figure out the actual source. So the more information that is there to obscure it, or the less information there is about the source, and that's acoustic information, of course, then the worse you're going to do at recovering your laryngeal source. Okay, so let's just kind of summarize what we've talked about. Not summarize. Get out of here, Sumerians. So we talked about how to measure the laryngeal source, right? There's a bunch of different methods. There's direct methods. There's methods of measuring the conductance, the impedance of the actual vocal folds. There are indirect methods. Well, that's an indirect method as well, but there's methods to look at just the output. So we can look at pneumotachography, we can look at the actual speech sound that comes through a microphone, which is, really the easiest, just because of the way that our technological world is set up. We've got microphones on everything, so we can grab a sound recording very easily. So we looked at also how to use the source filter model to estimate the laryngeal source. So of course, this ties into the second one, the use of the inverse filter, right? Because we have a sound source which goes through a filter which creates the output. And we use the inverse filter to go from the output back to the original source. We've also talked about what kind of quality we can expect. Our detective work of trying to figure out the laryngeal source would have based on different qualities of our imputations of finding the filter, of finding the inverse filter, and just the recording quality that we have to work with. Okay, that's it for this portion of the lecture.